Attendees are in listen-only mode.
Okay, you're on, Annie.
Hi. So welcome to this ICTM webinar. It is our third in a series of monthly webinars that we have been holding. And this one is a pretty exciting one from Craig Cullen. He's going to be talking about technology in teaching and learning math. And he's going to focus on a tool called GeoGebra. Craig is a former high school math teacher, a former ICTM board member, lots of other things, and currently an associate professor of mathematics education at Illinois State. So I think I'm going to go ahead and turn it over to Craig and let him get started. Oops, sorry about that. I'm flipping through all my stuff. Okay.
All right. Well, thank you very much, Annie, for the intro. And before I get too far, I'm hoping I can still hear you, Annie, and you can verify my screen's correct and you can see it.
Yes, looks good.
And hear me. Okay. So I just wanted to say thank you to ICTM for the opportunity to host this webinar. Special thanks to George Reese, Annie Forrest, and Sendel for pushing and getting these webinars started and to keep them continuing. So today I'm going to talk to you about, or what I want to talk about is the role of technology in the teaching and learning of mathematics. So although I'm going to try to do some things with GeoGebra, I hope that you pick some things up from GeoGebra or how to use GeoGebra if you haven't used it before. But I'm going to keep trying to come back to the focus for me, which is how should we be using the technology? So again, I'll do a brief intro for GeoGebra, but the purpose is to think about what we should be using technology for and how we should use it. So just a quick background for me, my journey. I've been teaching a technology course for the past 8 years now at Illinois State, focused on using technology to teach high school mathematics. And along the way I've been reading articles, I've been reflecting on things that I've done that I thought have gone well and things that have gone not so well. And I've also had the opportunity, which has been really beneficial for me, to go in and watch my former students teaching with technology, and to steal a phrase from a colleague, or maybe they were just teaching near technology. And so that was something for me that was really hard. I would see students say, "Oh, Dr. Cullen, you're going to come and see me teach next week, and I'm using technology. You're going to love it." And then I would see what they would do and what they were excited about, and didn't make me as excited. So it's caused me to rethink what should I be focusing on in the course. And so that's what I want to be talking about today. So at the start of the semester, a lot of times I talk with my students, and I say, well, what should we be doing with technology? Why should you use it? And I get a lot of answers that they don't seem to have a whole lot of meaning behind them. So things like, it keeps my students engaged. And you can have engaged students, but that might not be, they might not be engaged in good mathematics or good activities. So just to say it keeps my students engaged isn't what I think of as a good answer. Sometimes I'm in a school district where my students are, it's a one-to-one school district. All of my students have iPads, or we have these laptops or iPads or Chromebooks, so I better use them. Again, I don't think that's a good reason to use technology. So there's a couple of other ones in here. Students have grown up with technology, right? They're technology native. They're just more comfortable with it. Students think it's more fun. And the last one, at least I think, is a reasonable. It helps get at better conceptual understanding, but technology doesn't just get at conceptual understanding. What's important is how we use it. So the technology itself isn't good or bad or better or worse. It's how we use it. And so for me, I had to sort of rethink the course and what is it that I should be focusing on. It's helped me a lot. I'm sure that I'm not done making changes along the way, but what I have settled on right now is to think about 4 roles of technology, and that is the target that I put in front of my students throughout the entire semester. every week it's on my agenda that I hand to them. It's my it's the framework that I use for the course. And so those 4 roles of technology that I talk about, I talk with my students several times and sort of get them to think about finishing the sentence. When I use technology in my mathematics classroom, I will use it too. And I want to know what they're going to say to that. And so after going through, like I said, reading, reflecting, struggling, this is my list of 4 things. And so the first one is just promoting exploration. So technology is really good at letting us sort of play around with concepts, ideas. You can explore. And as you're exploring, we start to generate, and my students, I think almost everyone, starts to notice things and they start to say things. It takes a little bit of work, but I try to push my students to say, can you make a conjecture? So they start exploring, they make a conjecture. Then once they make that conjecture, the technology allows them to start testing that conjecture. I think it's going to be a line. And then they can start trying it and they can see, well, wait a minute, that doesn't look like a line. So then they might have to test and revise their conjecture. And then we step away from the technology and I say, okay, now can you prove it? So that's one place where I think technology is really useful, or one role that technology can serve. A second is to present and generate and connect multiple representations. That one I think needs less explanation there. The third place where I think technology is really powerful or useful is what I generally call dealing with data. Technology can be used to collect, it can be used to generate or analyze, organize large amounts of data. And so that's another thing. We'll probably look a little bit at those first 3 today. I don't know if we'll really look at the last one, but the last role that I talk about with my students is to have technology serve the role as 2T. So that's from an old article from 1980, I believe. Can't remember the guy's first name, but Taylor. He talks about technology serving sort of in 3 fashions, or 3 roles. It's tutor, tool, and 2T. And the tutor is you sit down in front of the machine and it's going to deliver some lesson to you. You're going to do, sorry, I turned off my email but not my phone. And there we go. So that the tool, tutor, and 2T, the tutor version, or the tutor role, is sort of you sit down in front of a machine and you're going to do some sort of set lesson that you're going through, and that's fine, but it's not an interest of mine. And the last one, though, the 2T one, is an interest of mine, and essentially one of the best examples of a 2T is when you sit down and you program a computer. And I don't teach computer programming, but the place that I do examples with a 2T, the technology serving the role as a 2T, is in Excel. So I have students go in and program Excel to allow a user to input an A, B, and C value, and Excel will spit out the solutions to a quadratic equation. So it's the students sitting down and teaching or programming the computer to do what they want. I think this is slides 7 through 14. I believe this will be made available to you afterwards. I'm not going to go through and read all of these things for you, but I've pulled some quotes from various articles about those 4 different roles, and so you can go through and see those, but I don't think that's a good use of our time now for me to read those to you. But I wanted it there so that you realize this isn't just me saying, here's what I think is good. This is from surveying this research, and people over and over again in articles are bringing up the fact that technology is good at these 4 things. So what I want to do today is get some discussion, well, no discussion I suppose, you're just going to listen, but I want to talk about using GeoGebra, and I'll try my best to keep on the focus. The focus for me is to say, how do we use this technology in a meaningful way? And for me right now, that answer is to do one of 4 things. It's to use it to generate the proof cycles, large amounts of data, a 2T, and to be connecting and presenting multiple representations. So again, I just sort of put this in here so you can have access to that link after the presentation. But that should be a website. You can probably Google geogebra.org and get here on your own anyway. But GeoGebra, for those of you who haven't used it, it's available on tablets. You can get it for Mac, PC. I played with it a little bit on my phone the other day. I'm only on an Android. I don't have an Apple phone. There's also an online app that you can run on the computer, or you can download it on your machine. So there's benefits to both of those. If you're in a school where you can't download certain things to your machine, you can just run GeoGebra from the online app. I've got a couple of other resources. Again, this is not stuff to be meant to be used today, but if you're interested in sort of finding out some more information or continuing to play, the first link there is a link to a video I made. It's about 15 minutes long. It's just me sort of opening up GeoGebra and showing you how to create the file that I'll start with. The next one is a link to a GeoGebra file. You don't need to look at it now, but later if you wanted to go back, it's sort of created so you can sort of tinker around with it if you want. The last thing is just a reference to an article that myself and a couple of other colleagues wrote. This is the problem that I want to look at today as an example comes from that article. So if you wanted to follow up on it, there's the reference so you can go and look at it. So today's task, I'm going to be using GeoGebra. I want to just explore perimeter and area, and I'm looking at rectangles. Again, the focus for me, I'll try to keep coming back to highlighting the roles of technology. And so, basic question to start with, I want to consider all rectangles with a fixed height, and I want to explore the measures of the perimeter in the area. And so I'm going to put that slightly into the background for just a second, and we'll come back to that. I'm going to do just a quick overview, if I can get it to come to the front. And Annie, hopefully you're still able to talk to me. So let me know if I've got my screen in a spot where you can see GeoGebra well. Make sure I'm not sharing a different screen than what I think.
Yep, no, it looks good.
Okay. So if you haven't seen GeoGebra before or used GeoGebra before, this is sort of how it opens. If you look at it, on the left-hand side here, I've got an algebra view. On the right-hand side, I've got a graphics view. And just some basic stuff. Again, if you haven't used this before, it can be a little frustrating to get started. But if you look down at the bottom, there's an input bar. This would be where you would graph a function. You can put things in down here. So you've got an algebra view, graphics view, input bar. Up at the top, you've got a collection of icons, and there's tiny little down arrows here. If you click on that, it opens up the family sort of icons underneath, and so now you can see you've got lots of tools. A lot of this is similar to Geometry Sketchpad if you've used that before. And then there's also things up in the top here, the file, edit, view, and tools, and I'll go through a couple of those things. So one of the things here, just to sort of get used to, that I think is different than what you might expect or what you might have experienced with Geometry Sketchpad, I can draw a circle here, and when I draw the circle, I also get information on the algebra side. And I just dropped a circle on the page, and when I did that, I got a conic section, or under the conic sections heading here, I got the algebraic representation for a circle. So again, thinking back to the roles of technology that I want to sort of highlight today, I'm already thinking about representations. I've got a circle over here, and I also have the equation of that circle over here. I can grab the circle and move it, And it's a little bit hard to see, but if you look at that, the radius, or the r squared over here, the radius squared, doesn't change when I move the circle, but you can see that the center is dynamically updated and connected to this side. If I change the size of the circle and leave the center, we can see that the radius is having an effect here. R squared is changing as I move this, as I change the radius of the circle. And you can change the sort of the size of this so you can see more or less sort of whatever you need. On the graphics page, you can click this little down arrow here. You can turn the grid on. If you just want to be doing geometry, you don't want coordinates on there, you can turn the grid on and off. Whatever you use to scroll on your computer, you can use to zoom in and out. And it's really quick. Nice example. If you just move on down into the input bar and type ax squared plus bx plus c. So I'm hoping, hoping you can see that well enough in the bottom there. I just typed that in. I didn't put y equals. I didn't put f of x or anything, and I just hit enter. And when I hit enter, it says, hey, I don't know what a, b, and c are. Do you want me to create sliders for that? And I'll say sure. And so as soon as I create the sliders, I get the graph. I've got the algebraic representation over here, and I've got my sliders over here, and I can start changing the graph, and I get reaction in both places. I get a reaction in the graph, I get a reaction in the algebraic version. And there's some really powerful mathematics tools in here. If I go down into the input bar and just type EXTR, it should pop up some options, and one of them is extremum. So I'm going to hit extremum, and then it asks me for the polynomial. If I look up here, it named the polynomial f. I hit f, I hit enter, it plots the extreme value for this function, and then I can do some things like I can right-click on it, and I can trace. And now I can sort of say, well, what happens if I start moving a? So this is ax squared plus bx plus c. If I start changing a, what will happen to the location of that vertex? And if I've traced it, I can start to see a pattern, I hope. So again, thinking about what is it that we should be doing with technology, I might ask a question now, make a conjecture about what happens to the location of the vertex in ax squared plus bx plus c when you start varying a. If you're relatively new to GeoGebra, you might also not realize that if you move up to the top and click on View, you could turn off the algebra if you just didn't want to see it, or if you didn't want your students to see it. But you can also turn on a spreadsheet. And again, all of this stuff is connected. If I right-click on this point, I'm going to turn the trace off, but I'm going to right-click on it, and I'm going to say Record to Spreadsheet. And I can limit that to 10. I can say Close. I can start varying A again, and I get a collection of ordered pairs over here. And when I click, if you watch the icons in the upper left here, if I click into the spreadsheet side, those icons change. And so now I can do a couple of things. One, I can select these ordered pairs. I can right-click on them, and I can say, let's create a list of points. And I get that list of points. It's dynamic. It updates if I start changing. And I can also do some analysis. So it doesn't make a whole lot of sense to analyze this stuff this way. But if I select a column over here, I should be able to do some one-variable analyses. And I can get a histogram. I can get a bar chart, dot plot. I can get a stem and leaf. It's really nice. I can also do real quick here. I can select both of these things. If I was trying to make conjectures about what this equation was, I could do two-variable analysis, and I could say, I think it might be linear. Gives me the linear regression. And there's a bunch of other tools in here, so if you teach any statistical things, it's really worth looking into this. I can split the screen now. I've got the residual plot down here, so I can see that looks pretty good. I can get the statistical information here. You can swap the X's and the Y's. You should be able to switch back over. I don't think I showed the dot or the stacked box plot. Again, they don't make any sense in this context, but you still have access to them. One last thing before I move on. Just again, this is sort of drink from the fire hose, quick intro, but you should at least see that this is here. There's 3D graphics view. If I click on this, I get a 3D graphics view over here. I didn't really mean to do that, but it's part of what I wanted you to see. All the things that show up in the XY plane over here also show up in the 3D version over here. So it's really kind of neat. And then I can draw, or I can construct things over here in this 3D version. You can create a sphere. You can change the sizes of that sphere. You can spin these things, look at them from different directions. You can construct other surfaces. I don't know if I'll be able to do this quickly and effectively, but so I drew that plane in, and once you've got that plane in there, you can then go ahead and construct intersections. So I can do the intersection of these surfaces, and I hope I got that to show up in my 2D graphic version over here. And I should be able to change, and I think now I'm running the GoToMeeting and the 3D graphics, and I think it just froze, so I'm going to exit out of that for now. But this is actually the intersection from that 3D part that shows up on the two-dimensional graph. So Annie, if there's any, I'm going to try to transition over now to sort of a quick exploration to sort of highlight the roles of technology. Now that we see what this can do, the question is, what should we do with this tool? And so this might be a good time. If anybody had questions, feel free to type them in, and I can try to answer along the way. But I'm going to transition. Yeah.
Okay. Yeah, there were a few questions. So one that was coming up from a few people was if you were familiar with like different tools like Desmos or Sketchpad, graphing calculators even, if you wanted to talk about like how a teacher might choose which tool is better, or what your preference is, or what you think the benefits are to one tool versus the other. So.
Yeah. I feel spoiled now, and so in terms of asking me about the graphing calculator, you know, I don't teach in a high school anymore. I just hate the little screens. If I have my computer with me all the time. So there is a convenience factor. If you have access to the graphing calculators, you know, the TI Inspire might be great. It doesn't matter to me what the tool is that you're using. I want to make sure we're focused on what are you doing with it. If you have a 4-function calculator, I think you can say, well, if I'm using this, how can I use this to get students to start exploring and generating conjectures and testing and revising those conjectures? I might get them to, you know, just sort of say, what's the biggest whole number you can get when dividing a 3-digit number by a 1-digit number? If I ask you that question with the calculator, you have a 4-function calculator. It's not going. You don't just compute right away. You have to think about what you're going to put into that machine. So again, my main focus is to say, I want to think about how we're using the tools. I don't care which tool you use. The reasons that I like GeoGebra is I have access to the spreadsheet, to graphing, to geometry, to the algebra. There's a CAS. There is some computer algebra system stuff that's available in. I didn't show that, but I haven't used it very much. But I have played around with it, and you can do some pretty powerful things in there, especially when you consider that this is a free software. Desmos, the teacher Desmos and student Desmos, that's a totally different thing to me. That is really powerful, really cool, and GeoGebra does not compete with that in my mind. But GeoGebra has some capabilities that I think Desmos doesn't have, and so that's one of the reasons that I use it. I have some mathematical capabilities and those different representations, I think, in my opinion, are easier to get those connections coming up. Anything else before I move on, or?
Just one more question kind of about that was somebody was asking, do you use this, like do students use this individually? Do you use this to show the class demonstrations? Sort of like what's the balance between teacher use and student use?
I think, you know, sort of start with what you're comfortable with. I encourage people, if you're still a little unsure, it's okay to just have it be you're in charge and you're doing the projecting up at the front of the room. If it means you're going to be more comfortable and you're not dealing with, you know, putting out 15 fires at once. But I do like it if I can get my students to be using this and letting them have access to the exploring and the mathematics. But if that's a big hindrance to you because you're still a little bit new and you're worried, I'd say go for it. Just put it up on the screen and you're in control and you have a whole class discussion, sort of similar to what I'll try to do today. Okay?
All right, one more that was specific to what you just did. Somebody was asking, is there a good resource for learning about the stats features that you showed?
I don't know. I mean, most of the time I just Google it and you can find a lot of stuff. I don't have any specific things that I look for, but the little bit that I've explored with the stats thing, it's really cool. You can do z-test, t-test. I haven't taught stats for a while now, so I don't remember all of the stuff that I'm supposed to be doing in there, but it does a lot of stuff. So if you're interested in that, I think it's worth investing the energy to learn it. Okay?
Sounds good.
All right. So again, if you're feeling frustrated about not being able to keep up with all of the stuff that's going on in GeoGebra, keep in mind my goal is I want you to just be reflecting and thinking about, once I learn how to use a tool, how is it that I can get the most out of it? And I sort of joke with my students and say, look, if I come in and see you and you say, you're going to be so excited I'm using technology today, and you take your worksheet and you project it on the screen, nothing's really changed. You're not really utilizing the importance or the affordances of technology. And so for me, I try to drill into my students' heads to be thinking about those four roles of technology. So I'm going to try to sort of talk through those or keep coming back to those as I talk through this example here. So I try to pick an example that could span a lot of age groups because I'm just not sure who would be here. So I picked a problem looking at a rectangle, a collection of rectangles, and we're just looking at perimeter and area. So I've had some fourth grade teacher that I know worked with one of her students on this task. I communicated back and forth with the student through email, and she made progress on the task. I've also used it with my college students, and it gets into some calculus concepts pretty quickly. So if you teach calculus, you're going to be seeing the concepts right away, I'm sure, but it's not overwhelming, I hope. So we're looking at how do the measures of the area and the perimeter of a rectangle compare? I just sort of have an open/vague question, and here's a rectangle, and I have it connected to a slider, and I can change the length, and I can change the width, or the height is what I have it labeled here. And so the question, if we remember back, what I really am interested in is saying, let's pick a height. So I'm going to pick a height of 1, and I'm going to leave it. And I'm going to vary the length. And the question is sort of, well, what do you notice about the perimeter and the area for this entire collection of rectangles? And I don't know about you, but I don't notice anything. And I think that's my fault. I think I need to have a better representation. And so thankfully technology is really good at offering representation. So I'm going to click on this button here, and when I do that, I get the measure of the perimeter and I get the measure of the area. So I've got 19.1 units and 8.55 square units for the perimeter and the area. And the question is, what do you notice about those two in relation to one another as I vary the length? And the idea again, the height can change, but then you stop and you look at that whole collection. So I could pick the height and move it to be 6.4, and then I could change the length, and I could say, well, what do you notice about the perimeter and the area? How might they be related? Anything that you might notice about them. And when I've done this in the past, when I do this with my students, many of them are, well, most of them are way smarter than I am, and they actually start to notice things and they start to tell me things. And I don't really expect that to happen, or I didn't expect that to happen the first time, but they start saying things like, well, when you move that length smaller and smaller, the area gets really small. And the perimeter gets small, but not as small as the area. And I sort of go, well, okay, I didn't expect you to see that, because I didn't see that until I put this representation up. So now I have another representation, and what I have is the perimeter and the area represented as dynamic lengths. So, and I should be careful, if I don't say that every time correctly, I apologize, but I really mean the measure of the perimeter is represented as this length, and the measure of the area is represented as this length here. It seems reasonable to call this the perimeter. It's sort of unwrapped, but I don't like calling this the area. Area is square units. But I have these measures represented here. And so now when I do this, I can see that as I get smaller and smaller, the area gets really small, but the perimeter doesn't seem to get quite as small, whatever that means. It's kind of vague right now, but we could test that conjecture now. So we've explored a little bit. We started to make a conjecture. Let's see if we change the height to be 6.5. Will we have that same reaction? And sure enough, it looks like the area seems to be getting smaller, much smaller than the perimeter when I have a really small or really short length. And depending on, again, I don't, in a relatively short presentation here, I don't have time for people to sort of explore on their own, but one of the things that my students start to notice, and I'm sure that some of you have already started to notice, is the perimeter right now is about 13.1. The length is about as small as I can make it before it turns to 0. So when I do that, the perimeter is 13.1 and the height is 6.5. And so now if we look at the fact that all these representations are on here and connected, I can actually look at the rectangle and see that, hey, maybe that makes sense, that the perimeter seems to be getting closer and closer to something that is about twice the height. So as the length gets smaller and smaller, as the length gets smaller and smaller, the perimeter is going to be dominated by these two height pieces. And so that perimeter seems to have a limit. So the limit, as I let L go to 0 for the perimeter, looks like it should be about 2h. The area doesn't act the same way. The area, as it gets smaller and smaller, the area, I have a product there, length times width. If one of them is going to 0, the whole product is going to 0. There's some other things that, as we start to look at this pair here, and I start to vary the length, what other things do you notice and wonder about? Well, again, I'd love it if we had time for you to just sort of play and sort of come up with conjectures on your own, but in the past, when I've worked with this, I've had students say, well, look at that, the area is small at first, but boy, oh boy, now it's really big. It's bigger than the perimeter here, it's smaller than the perimeter here, and that, of course, then makes me wonder about the place where the two are equal. And of course, I mean the measures. So if the perimeter is larger at first, and then the area is larger, it seems reasonable to think that maybe there's a place where the two are equal. And so I want to start exploring and say, well, how do I make the perimeter and the area equal? Are they always equal? These are conjectures that we can start, or questions that we can start asking, and we can start generating conjectures. And so it's pretty interesting to me, and maybe some of you have already thought about this, and this is not going to be a surprise to you, but it's really hard in this case to make the perimeter and the area equal to each other. In fact, it seems like the perimeter is getting larger and larger than the area, rather than the area catching up. And so the question that one of the questions that we start exploring as a group is to say, well, can you always make the perimeter and area equal, the measures of those two equal, by changing the length? Well, if the height is 1, I have a conjecture that the area is not going to catch up. But when the height is, we had 6 before, when the height was 6, it seems like we can. And so it makes me think, well, what about if it was 6 or 5 or 4 or 3? Where is it that the area will no longer overtake the perimeter at some place? So this representation is really powerful for me. This representation helps me start to see all these things and starts to make me wonder, and then we start turning these things into conjectures. So I'm going to do a couple of things here just to sort of highlight the representation capabilities here. If I go up and click, I can click on the axes, and now all of a sudden I have the perimeter and the area. I can move the perimeter up here to the x-axis, and then, that's close but not quite, there we go. Now what I might want to do is to say, well, what if as I move the perimeter and the area, as I was doing this before, I have no record of these pairings of perimeters with areas. And so I want to see if I can overcome that by offering a different representation. So I'm going to do that sort of geometrically here. I'm going to draw a circle with a center and radius, and I'll do this so you can see where I'm getting this from. The area measure here, it says the area is 6.6. That's actually called poly 1. So I'm going to create a circle, and I don't know if I mentioned this before, but I'm going to make a circle. If you come up and hover over here, if you hover over the circle tool, it will tell you what you need to do to use this tool. It says select a center point and enter a radius. So I'm going to select the perimeter endpoint here, and then I'm going to enter for my radius poly 1. And I'm going to hit enter, and it's going to create a circle for me. And then I'm going to use these tools here. I'm going to do a perpendicular line, and I'm going to do through that point and perpendicular to this line. I'm going to make an intersection point here. And there's other ways we could have done this, but now I'm going to do right clicks, and I'm just going to hide these objects. So I'm going to deselect show object, and then I can just put in a line segment, and what I've got now is the perimeter and the area. And the benefit to this representation is that I can sort of imagine, I can see the collection of all perimeters and areas. And of course we all know that there is no relationship between the perimeter and the area for a rectangle, but we have a fixed height here. So when we fix the height, it looks like the perimeter and area seem to have a pretty predictable relationship between one another. And so now, again, the role of technology for me, it's really good at providing representations so that we can start generating conjectures. And so it looks like we've got about maybe 5 minutes left before we wanted to sort of have time for questions. So I'm going to do a couple of things here that are going to be probably pretty quick, just so you see the capabilities of this. So please don't be frustrated if I'm going fast. But I can right-click here, I can hit trace, and I can start moving the length. And now I've got a nice collection, sort of a visual display. There's another representation of the pairings of perimeter, comma, area. If I do a quick scroll in and out, it'll erase those traces. I'm going to do something a little bit different now. I'm going to right-click on that. I'm going to turn the trace off. And then I'm going to go to View, Spreadsheet, and I'm going to right-click on this point, and I want to say record that to the spreadsheet. If you don't put row limit, you just collect so much data really quickly. I encourage you to always just click the row limit and sort of say what it is that you want, how many points. So I'll do 15 and I'll say close. And now I'm going to start varying the length, and I get a collection of, oops, it's a bad collection to have. So I get this collection of ordered pairs of perimeter and length. I can select this, and I think I'm okay. Let me check my options, labeling. Okay. So if I right click on this after I select it, I can say create list of points, and I get to see a dynamic collection of plotted points. And because I put this on a limit, it just sort of keeps scrolling through, and I get that collection of ordered pairs there. And if you're like me, you could probably sit and do this for 10 or 15 minutes and just watch those dots appear and reappear. It's really cool to me for some reason. But I want to keep going. I want to keep thinking about the perimeter in the area. So I'm going to move over here, and I'm going to say I want this to be equal to 2 times, sorry, that's not what I wanted in here. So I've got the perimeter in the area here. I could do that by doing that trace. And what I want to do is actually do one more option. So I'm going to delete this column. I'm going to delete this column. I'm going to stop recording this. I'm going to remove it, clear all traces, close. I just have to delete these two here now. And I can actually right-click and record the length to the spreadsheet. And again, I'll just do 15 points, close that, and hopefully I should get a collection of lengths. And then over here, I don't want the height. I have to be a little. I don't want the height to update, so I have to be a little bit careful here. So I'm just going to say equals height, and I get that height, and then I just want that height paired with all of these lengths. And then here I can do equals 2 times the length plus the width. This is a little bit of seeing the capabilities as the 2T. So I'm sort of programming this thing to compute the perimeter for me. Not a whole lot of difficult programming here, but I'm going to calculate the area in that second piece. And now I have the perimeter in the area. Copy that down. All of that is dynamic. It's going to update. And if I now take this collection, I can right-click on it. I can say create list of points. And I should get that same sort of dynamic list of points that I had. I don't have enough time to explain why I needed to do it that way. But if I take this collection of points now, again, thinking about using the technology to present representations, if I take now and add a line segment, or a line, sorry, that connects 2 of those points, I have a visual that will show me where sort of all of the ordered pairs will fall. And now I can start asking the question, well, what happens if I move the height? And as I move the height, you can see that the collection of ordered pairs are going to fall along a different line. And now, with one other sort of breakthrough, if we realize that this is x-axis and y-axis, which is the perimeter axis and the area axis, if I want to know where those two things are equal, I can go down to the input bar and put in x, and I'll get the line y equals x. And this is area. This is the line area equals perimeter, perimeter equals area. And it sure looks like when I have a height of 2.85, there will exist a length that will make the perimeter and the area equal. I don't know what it is yet, but it will happen. If I start changing the height, I can see that it will happen all of the times here that my collection of ordered pairs will cross this line, And again, think about the representations and what this affords you. I can now see that over here, those two lines are not going to intersect other than in the negative perimeter and area, which doesn't make sense in our context. So the question is, where is the break-even point? Where is it that you can make them equal and you can't make them equal, and where's the divider? And I have a conjecture that the divider between those two is 2. It looks to be that these two things are parallel here, and no matter how large I make the length, the area and the perimeter, the measures of the area and the perimeter will never be equal. So that's probably more than most people could stomach from me, I'm sure. And I wanted to make sure we have time for questions. So if there's Annie, if there's any questions that are coming through, or if there was any things that you think I might want to reiterate or re-comment on, or if you have questions, let me know.
Sure. Yeah, there were a few questions. So one person was asking about if you knew anything about dynamic worksheets in GeoGebra.
I don't. I know that it's really easy. So I'm not sure if the dynamic worksheets, I'm assuming they're asking about being able to input a value and have it sort of check something. GeoGebra Tube, I didn't mention that, but GeoGebra Tube is an incredible resource. You can just Google GeoGebra Tube. You can go there. You can view other people's files. You can also download them, modify them some if you need. You can upload your own materials there so that if you go to a computer lab, your students can all access your file. It's really easy to do. I know in GSP there was a way to do that, but I always struggled with it. It's really easy in GeoGebra. I believe if you just do File, it's an option that says Share. As long as you create a free account in GeoGebra Tube, I just click on Share, and it should take me right to and I just start entering the data. I put a title, and you can see my file here. If I uploaded this, you guys would all be able to just go to it and find it. So that would be the place that I would look.
Is that how you share something with your students, through that share function, or?
You are sharing it with essentially the world. You're sort of uploading it onto your GeoGebra Tube account, and you can make that the link to that then publicly available. I don't know if there's I believe you can make them public and private, sort of like you can on YouTube, but I don't think anybody's going to really steal my stuff, so all of my stuff I just make public. But that is a way that you can share those things. You can share that with anyone by just uploading on GeoGebra Tube. You don't have to have a GeoGebra Tube account to go to GeoGebra Tube and start scrolling around and start playing with other people's creations. You don't have to have GeoGebra on your machine to start playing with those. As soon as you go to GeoGebra Tube, you can search for, by different content or people's names, whichever, and then you can immediately start playing with that, even if you don't have GeoGebra loaded on your machine.
It's a free account, though, right? So do you recommend that students create an account as well?
I don't know if they would really need an account. I don't think you need an account to download the files. I've had my account for so long now, but I don't think you need I don't think they would really need an account unless they wanted to make their own files and upload them. So.
Another question was, is there a way for students to either collaborate virtually or share with their teachers their work, or just kind of that workflow question?
Yeah, I don't think there's a way like with a Google Doc where you'd be able to work on something at the same time. I could create a file and email it to you. I could create a file and upload it onto GeoGebra Tube. To me, when you start asking a question like that, that's where I think nothing compares to Desmos in my mind. You go to Desmos, there's that kind of sharing things back and forth and being able to watch your students as they're working. GeoGebra does not have that, as far as I know.
Okay, and then somebody was asking about using GeoGebra in middle school. Do you have any experience with that or seen that?
I don't personally, other than I worked just a little bit. My sister teaches fourth grade up in the Chicago suburbs, and she struggles a lot with feeling like she needs to differentiate for every child every day all the time. And so when I'm trying to help her stay sane, sometimes I'll send a question that a student can go sit and work on their own. And so I have interacted with one of her students in the past on this particular problem, you know, a modified version of this, but and the students seemed to do okay with it. She was in fourth grade, so I don't see why a middle school kid couldn't pick this up and use it with you.
An interesting question from somebody about how you think technology knowledge for teachers is best done. So do you think if a teacher wants to get better at using technology for math instruction, do you think traditional PD is best, a workshop model of PD, taking a formal class at a university? Like, how do you think teachers learn this kind of stuff best?
Yeah, I mean, to me, I don't want to sound like I'm selling the school option only, but for me personally, getting into a class where you're going to focus on it is one of the best, because you're just, you know, you're held accountable. We all have all kinds of other stuff going on. I'm sure there's lots of people that are listening to this with one ear and grading with the other arm. Right? We all have limited amount of time. There's all kinds of resources that you can go and look at on YouTube. You can watch people. They'll, you know, show you how to set things up. I like to just tinker with the stuff. So as soon as you get enough knowledge to start using GeoGebra, for example, I'd try to just play. I'd try to solve your own problem or pose a question and just start playing around with it. But again, to me, the part of learning the button pushing is important, but as soon as you feel comfortable with that, or even before that, you've got to be asking yourself, what is it that I'm doing with this? How is this different than paper and pencil? And that's what I was trying to show today, is this thing is a really good representations platform. I can represent all kinds of different things. I can then get my students to make conjectures. They can explore and make conjectures. You know, I think you can go out and sort of get a group of people at your school and try to be, you know, hold each other accountable and support each other, but it's definitely a challenge finding the time to learn these new things.
Definitely. A question about, because you kind of mentioned, you know, if your purpose is I want to have students make conjectures, test them, kind of discover some things, somebody was asking, do you recommend discovering it as a class? I mean, somebody kind of asked specifically like a smart board, like, and then have somebody come up and interact with it on the smart board. Do you pose the question and have everybody explore on their own, then come back together and synthesize as a group? Kind of like, how do you use this, like how do you plan a lesson to use it in a way like that gets at that? Yeah.
Right. And that's certainly it's always a challenge. For example, the problem that we were using today, I would try my best to have kids in groups. They're exploring, they're making conjectures. I'm circling the room, and I'm looking for them to be noticing the things that I want to notice. And then I'm going to be asking, and if every table has that, then I would just say, hey, everybody seems to have noticed this. Let's talk about it. And if not, then I hope I'm going to find one of the groups that notices, and I'm going to say, hey, this group has a question that they want to share, or they noticed this conjecture. Let's have them come up and show, and then we'll all explore that for now. Because, you know, it'd be great if they could all they were all self-motivated and they were going to discover their own theorems or conjectures and turn them into theorems, but we still have obligations for what we're going to cover. So to me personally, I would try to do groups. I then circle the room, and I've sort of got this list in my head or on paper of conjectures or things that that I want them to notice. And then when I find it, I'm going to ask that group or person to come up, share what they've found, and then we'll try to all do some of that exploring together.
Great. Let's see. I don't know. That was kind of all of the questions. Was there anything else that?
Yeah, I mean, I got a couple of quick things here. I don't know if you need time at the end to wrap out, but
Like a minute.
Back up now, right? So again, for me, I just wanted to come back to those 4 roles. I hope you got some things out of seeing what GeoGebra can do, but that wasn't my main purpose. The purpose is to say, how do you use that technology to promote exploration? How do you get people connecting and analyzing multiple representations, dealing with large amounts of data, and then you can also let that computer be a student for your students. I don't mean to imply that those 4 roles are the only ones, but if you're feeling like you need some focus, I would suggest those 4 as a focus. Just make sure you're purposeful with it. Make sure that you're thinking about what you're actually doing with the technology, not just saying, well, I can do this with technology. Just because we can doesn't mean that we should or that it's helpful. Make sure you keep that focus on the content, and then certainly willing to field follow-up questions if people have them. So there's my contact information. Then we've got about 2 minutes left, so I think I'll turn it over to Annie to try to figure out how to wrap all that up.
Okay, thank you. Let's see. I don't know how to share my screen now. Let me see. I'm still here in the platform. I don't know if George is still here, but me. Oh, here we go.
You're hiding in the background.
There we go. Okay. All right, so I'm going to kind of wrap us up here, but I just want to, first of all, say thanks to Craig. That was a really informative, and I feel like I learned a lot, webinar. So I just want to kind of end with saying, you know, if you're not an ICTM member, consider joining. It's by having members and being active and helping us out that we are able to bring webinars to you. If you are on social media, you can like the Facebook page for ICTM. It's actually under Illinois Council of Teachers Mathematics. You have to type in the whole thing, not just ICTM. But you can like us on Facebook. You can follow us on Twitter. And I think there'll be a survey coming out that would help us if you wanted to fill that out as well. Also, we want to remind everybody that the regional conference is coming in November, so save the date for that. And finally, next month we plan to have another webinar, so times, dates will be coming soon. If you have ideas of a topic that you would like to present on or an idea of a presenter, you can email Sendel, and his email address is there. So that is all I have. Thank you, everybody, for joining.
Thank you.
Thank you all. The recording should be available tomorrow.
Okay.
Okay. Good
Bye,
night.
everyone.